In this video, I want to have a look at something called the pigeonhole principle. So the basic idea is if I have, for example, 4 pigeonholes. So a pigeonhole is just a place where pigeons go. And then say I have 5 pigeons. My pigeons are flying. Okay, so I have 5 pigeons, I have 4 pigeonholes, and I want these pigeons all to go into the pigeonholes. Now there are lots of different ways that that can happen. But what the pigeonhole principle says is that there must be at least one box with at least 2 pigeons. So for example, I could put this pigeon in here, I could put this one in here, this guy in here, this one in here, and then I've got an extra one. So this one has to go into one of the boxes that already has a pigeon in it. So I could have 1, 1, 1, 2. Now that doesn't determine, the pigeonhole principle doesn't tell us how those pigeons are going in. It doesn't tell us that they're going to be distributed like this, but it does tell us that at least one of the boxes has to have at least 2 in there. Now, one of the other ways we could do it, for example, if we get rid of all those arrows, is we could have had, say, 3 of them in here, in this first box. This guy can go in here as well. Then we can have none of them in there, and we could have, that guy's already in a pigeonhole. Then we could have this guy come in here, and this one come in here as well. It can happen in any way, but we're talking about the overlap. So to write that more formally, if there are n pigeonholes and n plus 1 pigeons to go in them, then at least one pigeonhole must hold 2 or more pigeons. If we generalize that even further, if we have n pigeons and they're sitting in k pigeonholes, where n is greater than k, so we have more pigeons than we have pigeonholes, then there is at least one pigeonhole with at least n divided by k pigeons in it. So when we do this division, we'll often end up with a decimal, and we round up to the next number. We always round up. Let's have a look at a few examples. So our first example says, in a group of 100 people, what is the minimum number of people that share a birth month? So it's always good in these to identify what are your pigeons and what are your pigeonholes. So if we have 100 people, that's our pigeons. I'm just going to use P. Then we're talking about birth months. Now, there's only 12 possible months, so that 12 is our pigeonholes. The birth months is our pigeonholes. So we want to know the minimum number of people that share a birth month. We would go 100 divided by 12, which is 8.3 recurring. And again, we always round up. So therefore, we have to have 9 people that share a birth month, at least. So just to reiterate, this doesn't tell us what is happening. It's telling us that at least, as a minimum, so we're putting this limit on it, that there have to be 9 people who share a birth month. But for all we know, all 100 people could be born in January. We don't know, but we know that there's that limit of at least 9 people have to share a month. Our second example says we've got 9 cards drawn from a standard deck. We want to show that at least one suit has to occur 3 times. So again, we're going to identify our pigeons and our pigeonholes. So our 9 cards, they're our pigeons. And we're looking at the suits in this case. There's 4 suits. There's diamonds, hearts, clubs, and spades. So those 4 suits are going to be our pigeonholes. So if we do our 9 divided by 4, that's going to give us 2.25. And remember, we always have to round up. So if we round that up to the next number, which is 3, that means at least one of our suits must occur 3 times, because at least one of those pigeonholes, our suits, has to have 3 pigeons or cards in it. Our next example says a drawer contains 10 white, 12 blue, and 8 black socks, and these are all independent, they're not paired up. How many socks need to be selected at random to ensure that we end up with a matching pair? Now, the thing that often throws people off in these sorts of questions is looking at the number of socks in total. The fact that there's 30 socks in total is completely irrelevant to this question. What we want to know is that there's 3 colours. So those colours are our pigeonholes. So we've got 3 colours and we want to ensure a pair, which means we need at least one of those pigeonholes, one of those colours, to have at least 2 socks or pigeons in it. So what that means, if we've got 3 colours, we're going to need 4 socks. And the way you can think about that is if we had our white, our blue, and our black, then if I pick a sock out, maybe it's blue, the first one I pull out. Second sock might be black, the third one might be white, but that fourth sock has to fall into one of those categories as well. So we need a minimum of 4 to ensure that we have a pair. So we'll just write a little statement at the end saying that we need 4 socks, because if there are 4 socks and 3 colours, then the pigeonhole principle guarantees that at least 2 of them are the same colour. Okay, one last example. 6 netball teams play 16 games of netball. Show that some pair of teams must play each other twice. So if we've got 6 netball teams, if we're pairing them up to make so that they can play games against each other, we can do that in this many different ways. So we're going to go 6C2. That's going to tell us the number of different ways we can pair those teams up. And that would give us 15. Now, if there's 15 different combinations we can make, but we're going to play 16 games, then that tells us that at least one of those pairs has to occur more than once. So I've just written a statement at the end there to summarize. But again, and I know I've said this a few times, but I really want to stress that it doesn't mean that every team, every combination has played against each other once and then one of those pairs has played a second game against each other. That's saying that's the minimum of what could happen. But for all we know, they could have all played 2 games against the same team, but they haven't played every other team. Okay? So the pigeonhole principle sets some limits.